Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1884 stands as a pivotal moment in the history of the physical sciences, marked by the submission of a doctoral dissertation at Uppsala University that would fundamentally reconfigure the understanding of chemical solutions. The work, titled Recherches sur la conductibilité galvanique des électrolytes, and known in English as On the Dissociation of Substances in Aqueous Solutions, was the audacious product of a young Svante Arrhenius. His thesis, a formidable document of 150 pages, proffered a theory of such revolutionary implication that it was met with profound skepticism by the examining committee, earning him the lowest possible passing grade. This essay undertakes a rigorous and direct evaluation of the internal claims, methodological underpinnings, and logical architecture of this foundational 1884 work. We will proceed through a systematic analysis of the dissertation's core sections, examining evidence Arrhenius presented and the intellectual framework he constructed, thereby illuminating the profound perspicacity and the inherent challenges of his initial, comprehensive formulation of electrolytic dissociation. Our focus remains squarely upon the text itself, treating it as the primary artifact of a scientific revolution in progress, a document whose arguments possess a compelling logic that ultimately transcended the cautious reception of its first professional audience. Section 1. The empirical foundation of molecular conductivity. Arrhenius commences his dissertation with an exhaustive presentation of experimental data, a methodological choice, and grounds his subsequent theoretical leaps in the solid bedrock of empirical observation. The initial sections are dedicated to the phenomenon of galvanic conductivity in electrolytes. He meticulously tabulates measurements for a vast array of salts, acids, and bases dissolved in water at varying concentrations. The central claim advanced in this part of the work is that the conductivity of a solution is a property attributable to the solute, and that a more meaningful quantity for comparison is what he terms the molecular conductivity. This value, represented by the Greek letter lambda, is calculated by taking the measured specific conductivity and dividing it by the molar concentration of the solution. Arrhenius' primary assertion here is that as a solution of an electrolyte is progressively diluted, its molecular conductivity increases, approaching a maximum limiting value at what he conceives of as infinite dilution. He presents page after page of data for substances like potassium chloride, sulfuric acid, and ammonia, all demonstrating this characteristic behavior. The evaluation of this claim reveals its power. By normalizing conductivity to concentration, Arrhenius created a variable that exposed an underlying process independent of the sheer quantity of substance present. The consistency of the trend across disparate chemical compounds was his first piece of evidence for a universal mechanism at play. The internal logic is impeccable if the ability of a single molecule to conduct electricity were constant, then the molecular conductivity would remain flat with changing concentration. The observed increase demanded an explanation, pointing toward a change in the state of the molecules themselves upon dilution. The claim's strength lies in its empirical robustness. The data are extensive and the pattern is undeniable, forcing the reader to seek a theoretical cause for this systematic variation. Section 2. The postulate of active and inactive molecules. Having established the empirical puzzle of rising molecular conductivity with dilution, Arrhenius introduces his core theoretical postulate. He claims that in any given electrolytic solution, the solute molecules exist in two distinct states: a chemically inactive form and an electrically and chemically active form. The inactive molecules, he proposes, are the familiar, intact molecular units, such as a molecule of acetic acid or a formula unit of sodium chloride. The active molecules are responsible for the solution's ability to conduct an electrical current. The central argument of this section is that the process of dilution drives an equilibrium, shifting the balance from the inactive state toward the active state. At any finite concentration, a fraction of the molecules are active at infinite dilution. All molecules have transitioned into this active state. He introduces a concept he calls the activity coefficient, later formalized as the degree of dissociation and represented by the Greek letter alpha. This coefficient is defined as the ratio of the number of active molecules to the total number of molecules. He then makes a crucial connection. This activity coefficient, he claims, can be determined directly from his conductivity measurements. He posits that the degree of dissociation alpha equals the ratio of the molecular conductivity at a given concentration to the limiting molecular conductivity at infinite dilution. This formulation, expressing alpha as lambda divided by lambda infinity, is a stroke of genius. It transforms an abstract theoretical concept, the fraction of active molecules, into a quantity derivable from straightforward laboratory measurement. The evaluation of this claim reveals its elegance and its predictive power. It provides a quantitative, testable model for the behavior observed in the first section. The framework is internally consistent and offers a plausible mechanism for the previously mysterious dilution effect. The very idea of a dynamic equilibrium of two forms of a substance in solution was a significant departure from the static view of dissolved molecules, providing a conceptual toolkit to analyze the quantitative data he had so painstakingly gathered. Section 3, the unification of physical and chemical properties. The dissertation's next major argumentative thrust is perhaps its most audacious from a chemical perspective. Arrhenius claims that the active molecules responsible for electrical conductivity are the very same entities responsible for the characteristic chemical reactions of the solution. He argues, for example, that the strength of an acid is directly proportional to its concentration of active molecules. A strong acid, like hydrochloric acid, exhibits high molecular conductivity because a large fraction of its molecules are in the active state. A weak acid, like acetic acid, exhibits low molecular conductivity because only a small fraction of its molecules are active. He extends this logic to reaction rates, proposing that the velocity of chemical reactions, such as the inversion of cane sugar catalyzed by an acid, is determined by the quantity of these active molecules. To support this, he compares his calculated activity coefficients for various acids with the known data on their relative strengths and their catalytic effectiveness. He demonstrates a striking correlation, arguing that a single underlying property, the degree of dissociation into active forms, governs both a physical measurement conductivity and a chemical property reactivity. The evaluation of this section's claims highlights the immense unifying power of his theory. Hitherto, electrical conductivity and chemical acidity were treated as separate, unrelated phenomena. Arrhenius' work forges a direct, causal link between them. The internal logic is compelling if two disparate properties of a solution vary in direct proportion to a single calculated parameter derived from a third property. It is highly probable that this parameter reflects a real, underlying physical reality. His claim daringly redefines chemical properties like strength away from a vague, qualitative notion and toward a precise, quantifiable physical measure. This move represented a profound shift in chemical thought, suggesting that the core nature of chemical activity in solution could be understood through the lens of physics. Section 4, a theoretical explanation for Van't Hoff's anomaly in what may be the most brilliant and convincing section of the entire dissertation. Arrhenius turns his attention to the field of physical chemistry and the recent work of Jacobus Henricus Van't Hoff on colligative properties. Van't Hoff had demonstrated that the osmotic pressure of dilute solutions followed a law analogous to the ideal gas law. However, he observed that solutions of salts, acids, and bases exerted a much greater osmotic pressure, freezing point depression, and boiling point elevation than predicted by their molar concentration. To account for this, Van't Hoff had introduced an empirical correction factor, designated by the letter I, into his equations. For non-electrolytes like sugar, this I factor was approximately 1. For electrolytes like sodium chloride, it was closer to 2, and for others like calcium chloride, it approached 3. This I factor was a purely empirical fix, a number inserted to make the equation match reality, with no underlying theoretical explanation. Arrhenius' claim in this section is that his theory of dissociation provides the precise theoretical mechanism for Van 't Hoff's I factor. He argues that when a molecule dissociates into its active components, the total number of independent particles in the solution increases. Since colligative properties depend on the number of solute particles, this increase in particle count naturally explains the anomalous effects. He proffers a mathematical relationship: the Van 't Hoff factor I should be equal to 1 plus the product of the degree of dissociation, alpha, and the quantity, n minus 1, where n is the number of active particles produced from one inactive molecule. For sodium chloride, which he proposed splits into 2 particles, the equation becomes I equals 1 plus alpha. For calcium chloride, splitting into 3, it becomes I equals 1 plus 2 times alpha. This claim is evaluated as the masterstroke of the dissertation. It connects his theory, derived from electrical conductivity data, to a completely independent set of physical measurements from thermometry and osmometry. He could now calculate the degree of dissociation, alpha, from conductivity, use that value in his new equation to predict the value of Van 't Hoff's I factor, and then compare that prediction to the experimentally measured I factor. The agreement he demonstrated was remarkably good. This convergence of evidence from 2 distinct domains of physical science provided powerful corroboration for his dissociation model. It transformed the I factor from a mysterious anomaly into a predictable consequence of a single, unifying theory. Section 5. The contentious nature of the ionic state. Having built a formidable case based on conductivity, chemical reactivity, and colligative properties, Arrhenius finally addresses the chemical nature of his proposed active particles. It is in this section that he makes his most controversial claim, the one that met with the greatest resistance from the established chemical community. He postulates that the dissociation of a salt like sodium chloride in water results in the formation of free, independent, and electrically charged atoms or groups of atoms. He essentially proposed that the solution contained positively charged sodium entities and negatively charged chloride entities, which he would later, borrowing a term from Faraday, call ions. The internal argument rests on the requirement of his model to carry an electric current, the particles had to be charged. To explain the colligative properties, they had to be independent particles. Thus, a conclusion of free-floating charged atoms was a logical consequence of his entire framework. The evaluation of this claim, however, reveals the primary weakness of the 1884 dissertation from the perspective of his contemporaries. Arrhenius provided a compelling case that something was happening, but his explanation for what that something was seemed chemically preposterous. The prevailing chemical wisdom held that sodium was a violently reactive metal and chlorine a toxic gas. The idea that their charged atoms could exist placidly and separately in a beaker of water, without immediately reacting with the solvent or each other to form stable molecules, flew in the face of all chemical intuition. The dissertation lacks a satisfactory mechanism for how the immense energy required to break a stable chemical bond could be supplied by the simple act of dissolution, or for what stabilized these seemingly reactive charged species in the aqueous environment. A certain intellectual wit can be found in the historical irony. The very professors who found his physics-based arguments from conductivity and osmometry so alien were most offended by the part of his thesis that was most purely chemical in its implications. Arrhenius' claim was correct in its essence, but he lacked the modern understanding of solvation and hydration shells that would later provide the energetic and mechanistic explanation for the stability of ions in solution. His argument here was a brilliant intuition, a necessary conclusion of his model, yet it remained the most speculative and least substantiated part of his work at the time. Section 6. The dissertation's internal coherence and its subsequent interpretation. The final sections of the dissertation serve to consolidate the arguments and present a unified front. Arrhenius summarizes his thesis by re-emphasizing the triple correlation A degree of dissociation calculated from conductivity accurately predicts both the chemical reactivity and the colligative properties of electrolytic solutions. The internal coherence of the work is its greatest strength. It functions like a three-legged stool, with electrical, chemical, and physical data all supporting a single, central theoretical structure. Removing any one lead of evidence weakens the whole, but together they create an edifice of remarkable stability and explanatory power. The claim evaluated here is the implicit one that this unified model represents a truer picture of reality than the disparate and unconnected observations that preceded it. This coherence, however, was also what made it so difficult for his examiners at Uppsala to accept. Its conclusions were so far-reaching and so contrary to established chemical doctrine that they viewed the entire structure with suspicion. The famously low grade awarded to the dissertation was a direct judgment upon the perceived implausibility of its core claims, particularly the existence of free ions. The committee acknowledged the diligence of his experimental work but balked at the audacity of his theoretical conclusions. Subsequent developments, particularly the discovery of the electron by J.J. Thomson in 1997, provided the missing piece of the puzzle, a fundamental, subatomic particle of negative charge whose existence made the concept of stable, charged ions far more plausible. Later work by Debye and Huckel in the 1920s would further refine the theory, accounting for interionic attractions in more concentrated solutions, addressing some of the minor discrepancies in Arrhenius' original, simpler model. These later refinements, however, built upon the foundation Arrhenius had laid. They addressed the lacunae within his framework without overturning its fundamental principles. The dissertation's reception, therefore, serves as a fascinating case study in scientific progress, where the internal logical consistency of a new theory was initially insufficient to overcome the inertia of the prevailing paradigm. In conclusion, a direct and systematic evaluation of Svante Arrhenius' 1884 dissertation reveals a work of extraordinary intellectual synthesis and predictive power. Its claims, proceeding logically from a vast amount of empirical data on conductivity, forged unprecedented links between the physical and chemical sciences. By postulating the existence of active and inactive molecular states, Arrhenius was able to quantitatively explain the effect of dilution on conductivity. By identifying these active states as the agents of chemical reactivity, he provided a physical basis for the concept of acid and base strength. Most powerfully, by connecting his theory to the anomalous colligative properties observed by Van't Hoff, he provided stunning, independent corroboration for his model of dissociation, while his specific proposal of free-floating, charged ions strained the credulity of his contemporaries and lacked a fully developed mechanistic explanation for their stability. It was the necessary and courageous end point of his logical chain of reasoning. The 1884 work, in its entirety, stands as a testament to the power of unifying theory to bring order to a disparate collection of scientific facts. It laid the conceptual groundwork for modern physical chemistry, and its core claims, born from the mind of a single, determined researcher, eventually reconfigured the very language and logic of the discipline, proving that even a thesis awarded a fourth-class mark can possess the first-class genius to change the world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.